Hello everyone, and thank you for joining today's session on stability analysis and design of steel structures. Myself Surajit Ghosh, and along with me I have Bishotosh Prukasto. Both of us work in Bentley Systems in Engineering Simulation Group. In our previous session, we have discussed few advanced analysis methods like p-delta, buckling, and nonlinear analysis. If you have missed the previous session, you can still go through the recording which can be accessed using the same registration page. Just look for the first part. And today we are going to discuss how different international design codes like AISC and Eurocode handles the stability analysis and design criteria. Our today's session has two parts. First, Bishotosh will discuss about the stability analysis criteria as per AISC code. Then I'll cover how Eurocode recommends to perform stability analysis. So Bishotosh, let's start the presentation.
So in the last discussion on the stability analysis and the design, we discussed primarily on understanding of what exactly is the stability analysis, its importance, and the various analysis approaches. We have prepared this content with utmost effort so that our most of the user who are new or having sound experience in this subject can find it useful. And hence we try to cover it from the core theoretical background, eventually interpret them in STAAD model. So we try to keep the balance. For example, we can't show how to see the buckling factor in STAAD. We need to explain what exactly is this term and how this factor came into picture. And that will help the engineer to better use this feature. So in this session, we will discuss on the stability analysis and the design in light of the codal provisions and criteria. I will first cover AISC 360 code on the philosophy and the thoughts behind the stability design criteria in AISC 360 code, and then we will discuss on the direct analysis method, effective length method, and then I will walk you through the STAAD model to explain the implementation. Later, my colleague Surajit will speak on the stability analysis and design per Eurocode and its implementation in STAAD. So we have tried our best to elaborate as well as summarize such a big subject as per codal provision in a very lucid way. Now the stability analysis and design criteria is specified in the chapter C of the AISC 360 code. Now I am using the term 360 only because this chapter number is almost same in 2005, 2010 and 2016 edition of this code. So fundamentally mostly same except slight amendment. Now, the code mentions three important subjects that will cover and ensure the proper stability analysis and design. These are like general stability requirements, calculation of required strength, and then calculation of available strengths. The general criteria means the concerns that must be taken care of that affects both the system or the frame stability and the member stability. These concerns are taken care of while determining the required strength and the capacity limit state. So the basic and the general requirements are flexural, shear, axial, member deformation, and all other component and the connection deformation that contribute to the displacement of the structure has to be taken care of. Second order effect, including P large delta and P small delta, has to be considered. We need to consider the initial geometric imperfection like out of plumbness or member out of straightness. Then stiffness reduction due to partial yielding accentuated by the presence of residual stress has to be taken care of. And finally, the uncertainty in the system member or the connection strength and stiffness. So the design code nicely and effectively handles all the concerns that affects the member as well as the system stability by determining the capacity and the demand and then finally compare and interact them. So the factors affecting the member stability mainly are the initial member imperfection, which is the member out of straightness, and the inelasticity accentuated by the residual stress. So AISC code take care of these factors while determining the capacity in chapter D through K. For the system stability, the factors like initial system imperfection, which is the initial out of plumbness of the system, and the reduction or the adjustment of the stiffness due to initial member out of straightness and the residual stress. And it is covered in the clause C2. Now, basically, AISC simply using the combination of numerator and denominator of the interaction equation to address the concerns. So let's summarize the general requirements as outlined in the code. So I have summarized them in a table for better understanding. Most of the concerns and the requirements are taken care of while determining the required strength, but just three factors that affects the stiffness and the strength are: first, member initial out of straightness; second, inelasticity due to the residual stress; and the third, the uncertainty factor. And these three factors impact both the member capacity and the structural response. So these concerns are taken care of while calculating both the member available strength and the required strength. And this understanding shown in the table is very important, and this is the basis of the philosophy of the current stability analysis and design in AISC 360 code. So that is the reason that I might refer this table over and over again in my presentation. Factors affecting the member stability, and it is considered in determination of the available strength. Now the available strength is determined by the chapter D, E, F, G, H, I, J, K, whichever is applicable, considering the uncertainty factor like phi and omega. So let's see the factors that affect the member stability. So the column curve has been developed that has the factors and concern included. They are like yield limit, buckling limit state based on the length, imperfection due to the initial out of straightness, partial yielding accentuated by the residual stress, and the and restraint conditions. So if we have the equation or column curve having all this consideration, then it will guarantee the proper determination of the member stability and the available strength limit state. So let's quickly see how these factors were considered in developing the column formula or the column curve. Initially, the column capacity was only based on the member full yielding. It's simply squishing the column by a concentric axial load, and without the consideration of buckling effect, we determine the relationship between the applied load and the limit when the full yielding develops. So it's a very simple equation, and it's very simple. The arrangement and everything is very simple. So we have considered the full yielding, but if we keep on increasing the member length, the member will certainly buckle. Now, next we move to the second consideration, that is the buckling equation formation and its inclusion in the column curve. So the great mathematician and physicist Leonhard Euler, around more than 200 years back, found a relationship between the column length and the buckling load. So every one of us quite familiar with this fundamental equation. So as the length increases, the member axial load bearing capacity decreases. So the Euler curve is somewhat like this until it crosses a point where the full yielding starts. So the column curve is modified like this, and few assumptions that are considered. The column is perfectly straight and elastic, and both the ends are pinned. So the full yielding and buckling limit state based on L over R is included in the column curve. But Euler didn't consider some other factors like initial out of straightness of the member, residual stress effect, and the different end restraint condition. So let's see how they impact the member stability and how we can include them in the column curve. As mentioned and explained in our last webinar, that every real life column has some initial imperfection like out of straightness. This out of straightness affects the stability response against the applied load in a column. This initial imperfection triggers the nonlinear response, and the column would in reality undergo displacement, and theoretically, no matter whatever is the initial eccentricity or the imperfection, the maximum crippling load would be the same, and it will asymptotically touch the bifurcation limit at infinite displacement. But in reality, we have to consider some limit on the displacement. We can't go to some infinite displacement. So after limiting the maximum allowable displacement, the corresponding allowable buckling load can be projected and calibrated, which is less than the Euler load by some factor. And AISC, after having series of rigorous testing by several great structural engineers over the decades, calibrated the allowable buckling load limit for a column with an initial out of straightness of about L over 1470. And statistically, they came up with a calibrated factor of 0.877. Now, due to the time limitation, we could not discuss more on this, but maybe in some other webinar, we'll throw some light on this detailed derivation. So that's the reason in the ASC column curve equation, we can see the buckling curve as 0.877 times the actual Euler buckling load. Now, remember this factor. You might be wondering why we have to show this factor in this equation. Actually, it has the significance. We'll see later on in direct analysis, assumption, and formulation. This phenomenon is vital, the residual stress. The hot rolled steel section goes to several stress variation as the function of temperature change. See this picture, the rectangular section is being hot rolled from its manufacturing unit. Now at this stage the center portion is glowing more than its surrounding, and this is because of the outer portion owing to the vicinity of the cooler air. So it cools faster and then contracts. So over the time when the central portion also cools down, the outer portion has already been set, and at this stage and at this portion, as the contraction is being restricted, the tensile stress is developed. And to keep it in equilibrium condition, the outer portion conversely develops the compressive stress. So this stress pattern or behavior is known as the residual stress. Now, this also happens in the hot rolled wide flange section. You can see in this picture. The flange tips and the web center, which has a higher surface area, cools faster than the web flange junction. So here the tension is developed in that junction and the compression in the outer flange tips and some portion in the web center. Now this affects the structural stability and strength. So as you can see here, the stress is varying from compression to tension as it is moving from outer flange tip to the inner central junction. That means the outer flanges already have residual compressive stress and they will reach the yield stress limit much earlier than the rest of the section. Now, as some of its portion has already been yielded once it reaches the yield limit, it will lose the axial stiffness and then the remaining portion has to bear the total force. Again, some portion of the unyielded portion will start yielding and this will go on. And this is an inelastic deformation which starts from the extreme flange tips. So the load versus axial deformation pattern is not varying linearly. It is material nonlinear due to the inelasticity. Now, these yielded portion has insignificant E value and this starts when the stress reaches almost 50% of the yield stress limit. This has been assumed in AISC code and there is a different relationship between stress versus strain. We can't call it the normal elastic stress versus strain relationship. We can call it the tangent modulus. To know the exact derivation, you may refer to the book on stability of structure by Galambos and Surovec. Now, this relationship has got a factor called tau b. You must have seen it if you have used the direct analysis before. So we are slowly moving towards that direction. The loss of E value also significantly affects the effective EI value, that is the flexural rigidity of the member, because the member has been softened and its flexural rigidity has been degraded. Now the only concern left with us is the end restraint condition of the column. Now please note that the Euler column is based on the condition when both the member ends are pinned, and that is why the buckling load is plotted against L over R ratio, and the K value, that is the effective length factor value, is not brought in the curve. Now the end restraint condition affects the member stability significantly. For a simple member and support condition, it's very simple as shown in the table. One can use the differential equation and set the various boundary condition and deduce the crippling load and the corresponding effective length factor K. But in the real life structure, we are not fortunate enough to get such kind of end restraint condition for every member. Now, take the example of a building frame structure where members are connected with another members, and these end nodes are not assigned externally by any support conditions as shown in this table. So then our life starts getting tougher. So it's not that simple to determine the effective length factors for such members. So over the time, various structural engineers raked their heads to find some solution, and then they started testing several columns in laboratory with and restrained with various support stiffness, and then came up with some factor like this. And we can see these factors while using the AISC alignment chart for determining the K value. So now we got the K value from all those exercise and then plug the same in the curve. So the effect on the member strength and stability due to the initial out of straightness, partial yielding due to the residual stress, and the end restraint conditions are accounted in the column curve. And finally, AISC came up with this column curve for determining the column strength. Now, here you can see the portion where the transition between the buckling limit and the full yield limit is smoothened. And this is because in reality, the inelasticity accentuated by the residual stress starts developing much earlier around this zone. So now we have the AISC column curve, which accounts for all the required factors that affects the member stability. So we have discussed so far on the member stability by determining the member available strength. Now we will see how the factors that affect the system stability and discuss on how these are accounted for in determination of the required strength. So let's quickly see the factors that we need to address and include. First, all the deformations need to be included. Second order effect including P small delta and large delta has to be considered in the procedure. Initial out of plumpness of the system and initial out of straightness of the member has to be considered. Stiffness reduction due to the residual stress and the uncertainty. So these all has to be considered while we are determining the required strength. So these methods for addressing these factors are mentioned in the chapter C and the appendix 7. So ASC 360 specification 2005 permits the use of any method that determine the required strength for determining these factors that affect the system stability. But the three standard approaches based on the elastic analysis as specified by ASC are like the effective length method, the direct analysis method, and the first order elastic analysis method. So we will discuss them in detail. So few of the characteristics associated with the effective length factor are mentioned as below. This is a traditional approach where we need to find the effective length factor by the alignment chart or the effective length by any procedure like buckling analysis. This method also requires the consideration of the second order effect like P large delta and P small delta. Now, in AISC pre-2005, this method doesn't require the consideration of the notional load, but from 2005 onwards, AISC specifies using the minimum notional load. Please note that the reduction in stiffness due to the residual stress is not considered in this method. And this method is permitted to use only if the B2 factor or the maximum drift due to the second order analysis to the first order analysis is less than 1.5. Now the next method is the direct analysis method, which most of you might be waiting for. Now this is a very interesting method, but for understanding it better, Let's see how the direct analysis method evolved and came in AISC 2005 and its later editions. It is very important to understand why and how the direct analysis was developed. Yes, maybe some of you are aware of the philosophy, but while we interacted with our users in past, most of them requested us to elaborate the theory in detail because engineers know how to run them in STAAD, but they're quite unclear of its exact objective. So for this, we need to go to AISC pre-2005 practice. In pre-2005, although the second order consideration was required, but there was no requirement of the consideration of the system imperfection like initial out of plumbness and the stiffness adjustment due to the presence of residual stress, which significantly impacts the structural response. Now let's bring the table that we saw in the very beginning of the session. So in pre-2005, we were considering the initial geometric imperfection and the inelasticity due to the residual stress in the calculation of the member capacity. Just recall our discussion on the column curve consideration. But in pre-2005, we were not considering its effect on structural stiffness and the corresponding response. In other words, we were determining the member capacity correctly considering these factors, but we were not considering its effect on the stiffness while analyzing the structure to determine the required forces. So performing the analysis to determine the required strength is not compensating the determination of the available strength. So this gap or limitation was compensated indirectly by the K factor through its conservatism. Let's take a simple frame, for example, whose column and moments are released, and this frame can undergo side sway. So here, as the frame is prone to the side sway, creating P delta secondary moment. In the ELM method, where we are considering the K factor, so K equal to 2 is used to decrease the buckling load capacity due to the side sway action. Now, if we see the structural behavior of this problem in depth, what we are indeed doing is we are decreasing the capacity due to the side sway action by considering the K equal to 2 value and again amplifying the required moment due to the side sway action by doing the second order analysis, which is a conservative and not the real practice to capture the real structural behavior. So post 2005, K was set to unity. So K value is 1. Also, as mentioned in my last webinar, that as the buckling is not real, as it is not dependent on the initial imperfection, whereas the response due to the second order analysis considering the initial imperfection is always real and practical. So the new method evolved by fixing the K equal to 1 and calculating the amplified moment by the second order analysis with the initial out of plumbness mimicked by the notional load and the reduced stiffness due to the residual stress. And this new method is known as the direct analysis. So the direct analysis method addresses all the requirements as mentioned by the AISC code. Let's discuss them. First one is quite obvious as all the deformations and the displacement has to be considered in the analysis and STAAD care of all those deformation and displacement while performing the analysis. Second is the consideration of the second order effect by considering the P large delta and P small delta. Now that is also being considered by STAAD while you are performing the direct analysis. While you perform the direct analysis, STAAD at the background runs the P delta analysis. Now third is the initial out of plumbness or the initial imperfection. Now AISC specifies two different methods. First is called the direct modeling of the imperfection, where you can directly model the initial imperfection by modeling the initial deformation at the member intersection point, and for this you can refer to the code for more details. Second one is the use of notional load. Now this method is relatively easier and widely used by the engineers. Here the engineers need to reproduce the specified initial out of plumbness of the system indirectly by applying the equivalent lateral load as a fraction of the gravity load being applied at the same level, and this equivalent lateral load is the notional load. That means whatsoever the additional secondary moment that would have been generated if the initial out of plumbness would have been there, the same secondary moment would be generated by the notional load. So here you need to model the structure straight as usual and apply the notional load of 0.002 alpha times y sub I, where the alpha is the factor like phi or omega depending on the method you use, ASD or LRFD, and y sub I is the gravity load acting at the ith level. Now 0.02 is equivalent to L over 500. That is the initial out of plumbness as standardized by the AISC code. And this notional load is to be included as the minimum lateral load for all the gravity only combination and all the other lateral load combination, where the second order drift to the first order drift ratio is greater than 1.7. So the bottom line is the notional load is ensuring that the structure is being destabilized for all the combinations, and which is very much necessary for performing and capturing the proper second order effect. Now the next one is the stiffness adjustment due to the residual stress. Now, this is one of the vital factors that is considered in the direct analysis. We have discussed that due to the residual stress, the member capacity is already modified in the column curve. You can recall the partial yielding that we discussed earlier. Now, we have to consider this effect on the stiffness and the structural response as well. Not only the adjustment of stiffness due to the residual stress, but also for the consideration of the initial member out of straightness and the uncertainty factor. These three factors we already considered in the determination of the member capacity. So we have to compensate the same in determination of the required strength. So the direct analysis uses the stiffness modifier, which is zero point 0.8 times tau b. Now 0.8 is a blanket reduction for all the members contributing to the stability of the structure, and an additional tau b factor shall be applied to the flexural stiffness of all the members whose flexural stiffness are considered to contribute the stability of the structure. Now, tau b that we discussed earlier as a tangent modulus, which depends on the percentage of the actual load level to the yield limit, that if the load level exceeds 50% of the cross-sectional compressive strength, the tau b factor changes with the applied load. And below that load level, its value is 1. So you can see the relationship in detail. Now, so a very interesting fact we can see here. So we can correlate these factors with the same consideration that we have done in the column curve equation. For the frames with slender member where the limit state is governed by the elastic stability, the 0.8 factor that we are considering now on stiffness is roughly equivalent to the safety margin we used in the column curve equation while determining the member capacity, which is around 0.9 times 0.877 of the Euler crippling load. Now 0.877, as we discussed, is the factor that we use to consider the initial out of straightness, and 0.9 is the uncertainty factor. So this product comes around 0.79 times PE, that is crippling load, which is roughly same as 0.8. So we can see that the both the factor, that is factor that we considered earlier for the initial out of straightness and the uncertainty factor, are currently included in the stiffness adjustment as well. Second is for the frame with intermediate or stocky columns, and the 0.8 times tau b factor reduces the stiffness to account for inelastic softening prior to the member reaching its design strength. Now the tau b factor is similar to the inelastic stiffness reduction implied in the column curve that we've seen before to account for the loss of stiffness due to the high compressive load. And we have seen that when the load level exceeds 50% of the yield limit, then we started seeing the curve taking a different path, the inelastic path. So this zero point 0.8 factor accounts here for the additional softening under the combined axial compression and the bending. So we can see here that The stiffness that is being adjusted in the direct analysis for calculating the required strength includes the three factors: the uncertainty factor, the member initial out of straightness factor, and the stiffness reduction due to residual stress. And this is the same as we considered in determining the member capacity. So the required strength and the available strength are being compensated. So the direct analysis method addresses all the stability requirements in a very practical way. There is another method which is known as the first order method, used only when the ratio of the second order drift to the first order drift is within 1.5 and alpha times p over py is less than 0.5. So we will not discuss much on this method because this is just derived from direct analysis, and we can use directly the direct analysis instead of that, because in direct analysis there is no such restriction. So now we will quickly see the difference between the direct analysis method and the effective length method. So here you can see, although in AISC code and the design guide 28 you can find the tabulated list, but I have sorted down the main difference, fundamental difference between these two approaches. So first one is in ELM method, one can only use if the ratio between the second order drift to the first order drift is less than 1.5. Whereas in DM, there is, or direct analysis method, there is no such restriction. In effective length method, one has to calculate the K value, which is a very complex task because there are 10 different types of structural considerations that are to be satisfied to get a reliable K factor if you calculate them by the alignment chart. But in reality, these conditions are seldom met. Whereas in direct analysis method, there is no requirement of K calculation because we are assuming the K as 1. Third is in the effective length method, there is no such stiffness adjustment as we have discussed earlier, whereas in direct analysis method, we are adjusting the stiffness. So let's see how to perform the direct analysis in STAAD with a simple model. The direct analysis is to be first defined from the definition option. So once you click on the direct analysis definition tab, you can see a dialog box pops up. So this window will have the parameters like flex, FYLD, axial. These parameters are the initial input criteria for the direct analysis. First, the flex parameter. This is for controlling the flexural rigidity. This parameter represents the tau b involved in the reduced flexural stiffness calculation, that is 0.8 tau b times EI. Now the default value of this is 1, but a user can change this default value. So if you keep the default value of 1, it would be treated as the initial tau b factor. Now in the consequent iteration, the tau b would be calculated based on the actual axial stress in the member over the defined FYLD value. Second is the FYLD parameter for defining the yield stress limit. By default, its value is 36 KSI. So please note that the dialog box doesn't show any current unit system. So please make sure you set the current unit system in KSI from the input editor file by simply adding kpinch just before the direct analysis definition. Now this FYLD would only be used in the tau b calculation, and it has no role in the design parameter. Third is the axial parameter. As the code doesn't specify any variable reduction coefficient for reduced axial stiffness, 0.8 is used for constant reduced axial stiffness determined as 0.8 times EA. Now our next step is to apply the loading arrangement in the model. First, you need to define the gravity load cases and all the lateral load cases if there is in the model. So I'm taking only the gravity load case here. Now, as per the AISC code, the notional load of 0.002 of the gravity load case of that label must be included in the combination case. Also, you need to add the notional load in other combination cases which has the lateral load as an additive value. The idea is minimum notional load if the second order drift to the first order drift is less than 1.5, and additive if the ratio is greater than 1.5. Now in this model I have only taken the gravity load, so I am using it as a minimum notional load for its combination case. Next point to note is that as the direct analysis is a nonlinear analysis, you should use the repeat load instead of the load combination option. So the repeat load case calls the gravity load and then define the notional load. Program would automatically compute the notional load from the gravity load correspond to that flow level. The third step is invoking the direct analysis command. So the first option is LRFD or ASD. Now, as it is essential that the analysis of the system be made with load factored with the strength limit state level, because we are using the direct analysis and the non-linearity is associated with the second order effect. So we are already considering that it is LRFD. So if you select LRFD, the STAAD automatically multiplies the loads internally by 1, and the results are subsequently divided by 1 to obtain the design force. So there is no change. Whereas if the ASD option is selected, this load level is estimated as 1.6 times the ASD load combination. So STAAD automatically multiplies the loads internally by 1.6, and then the responses or the results are subsequently divided by 1.6 times to obtain the design force. Now next is the tolerance limit for tau b and displacement. Now when the tau b is iterated, STAAD is checking if the next iteration is required, even if the ratio of the axial stress over the allowable stress exceeds zero point 0.5 as defined in the code. So if the difference between the consequent tau b is too small and within the tolerance limit, the iteration would stop. So it is advisable that you set the default tolerance limit very small, preferably zero point 0.1 for refined and better result. Similarly, you can set the displacement limit. Next, the two set of iteration limits you may adjust here. One is a tau b iteration limit and second is the p delta iteration limit, because in this model both the tau b and p delta are being iterated if needed. However, you may keep the default value, as in most of the cases the iteration converges within this default limit. Finally, the instruction to consider the reduced EI and performing the tau b iteration. So again, as we are doing with all the required assumptions and consideration as per the code, so you may keep them checked on. Now after performing the direct analysis in STAAD, you needn't have to use the KY, KZ, LY and LZ parameters, because the default K equal to 1 and the default L as the member length are to be used while determining the member capacity calculation. Now, one important point to note here is that direct analysis is performed only for the strength and stability limit state, and its reduced stiffness should not affect other conditions like drift, deflection, vibration, or the period determination. So if you are performing both the stability and strength design by the direct analysis, as well as performing the serviceability check or the model calculation in the same model, then you need to use the perform analysis first, followed by the change command, and then the direct analysis command to reset the stiffness matrix with the modified reduced stiffness. So now I am handing over to Surajit. He will carry on with the stability analysis and design criteria per Eurocode and its implementation in STAAD.
Thanks, Bishwa. Hello, everyone. I'll now discuss the stability analysis criteria according to Eurocode. As Bishwa mentioned, in AISC code, performing direct analysis method ensures the stability of the structure, considering all the conditions like imperfection, material nonlinearity, stiffness reduction, and so on. Now in EC3 code, there is no such method available as direct analysis. Rather, there are several sections mentioned in this code which handles the stability analysis and design criteria. So, if you want to perform stability analysis, you need to consider and incorporate all these guidelines. Before going into the details, let's check what are those criteria. First, we need to consider the global analysis criteria as mentioned in section 5.2. This will consider the effect of both deformed geometry and also the structural stability of frames and braces. Also, we need to consider both global and local imperfection as mentioned in section 5.3. Now, Eurocode suggests that we can either perform first order analysis using initial geometry, or we can go for second order analysis to consider the deformation of the structure. Which analysis method needs to be considered for a structure that depends on several criteria. For example, we can perform both first order and second order analysis and compare the results. If the second order effects are negligible or doesn't have any significant effect on the structure, then we can use first order analysis. Frankly speaking, analyzing a model twice and compare the results is a very tough and time consuming task. There is another method which is easier to follow by checking the alpha CR value. For elastic analysis, if the alpha CR value is greater than or equals to 10, then we can go for first order elastic analysis. Now have a close look on the alpha CR value, which is the ratio of design load by elastic critical buckling load. This is nothing but the buckling factor. So if we perform buckling analysis and check whether the critical buckling factor is greater than or less than 10, then we can easily find out whether we should perform first order analysis or second order analysis. As we know from our previous day discussion that buckling factor close to 1 means the structure is most susceptible to global buckling due to the applied load compared to the higher buckling factor. So if the chance of buckling is high, then code suggests that we should go for second order analysis where the deformed shape is taken into account during analysis. So to fix the analysis method, the first step is to create a factored dead and live load case for which we need to perform the buckling analysis. Once the analysis is performed, we can check the buckling factor in the post-processing table or in the output file. If the buckling factor is greater than or equals to 10, then for that model, we can use perform analysis command which performs the first order elastic analysis. And if the buckling factor is less than 10, then we should go for the second order analysis. For example, P delta analysis which considers both the small delta and large delta. Now the analysis method is fixed and we have to ensure the stability of the frames. This should be ensured considering both the second order effects and also the imperfection. Eurocode suggests different approach depending on the type of frame. Instead, imperfection is not considered during structural analysis and hence clause 3a cannot be followed. So we have to consider the stability of frames following clause 3b and clause 7b, partially by global analysis, whether first or second order analysis is selected, and partially by the checks suggested in section 6.3, which depends on the buckling resistance of members. For any member which is designed per EC3 code, section 6.3 is checked for buckling resistance, and combining the analysis method selection and checking the buckling resistance ensures structural stability of frames. So no extra inputs are required here. Now coming to the imperfection. Code suggests that we need to consider all kinds of imperfection in the analysis like residual stress, lack of verticality, lack of straightness or flatness. The overall imperfection can be categorized as global imperfection of frame and braces, which is covered under section 5.3.2 and 5.3.3, and local imperfection of individual member, which is covered under section 5.3.4. If we consider section 5.3.4 for local imperfection, then we can find that the local bow imperfection of individual member are already considered under the formulas provided in section 6.3. As this check is already considered, so no additional check is required for the local imperfection. For global imperfection, it is for the overall structure and needs to be considered properly. There are two methods by which we can consider this global imperfection. First one is to model this imperfection. So we need to find out the initial imperfection like how the frame is already tilted and other conditions, and need to model the structure considering all those effects. This is a lengthy and erroneous process as finding out the initial imperfection accurately is very tough, and also modeling all those imperfections are time consuming. There is an alternate method where we can model the structure without considering the imperfection. Means during modeling we are considering the structure to be straight without any imperfection, and during application of load along with all the gravity load we need to apply an equivalent horizontal load which is in proportion with the applied vertical load. as if we are pushing the structure laterally to cause the imperfection. During structural analysis, this initial showy imperfection will be considered, and instead, this horizontal equivalent load phi into NED can be applied using the notional load feature. I will come back to this in details. This is the representation of the equivalent horizontal force. So the structure is considered to be straight and we are applying an initial equivalent horizontal load along with the gravity load, and combined effect of these loads will be considered during frame analysis. Note that this showy imperfection needs to be applied in all horizontal direction but once at a time. So we cannot apply the equivalent load under a single load case for all the direction. Two separate load cases are required where each load case will represent a particular direction of imperfection. To consider and apply the global imperfection in the model, we have to calculate the initial showy imperfection value. This phi value needs to be calculated using equation 5.5 mentioned in the code, and the calculated factor should be specified as notional load factor. If we check the full equation, we can find that phi value depends on the height of the frame from the base as well as on the number of columns present in that row. We can check the height of the frame from the model. For m value, which is the number of column in the row, this can also be calculated from the model, but there is an additional condition. Code suggests that only those columns should be considered which carries not less than 50% of the average vertical load on the column in that plane. Let's take an example. For this frame, there are 4 columns and the total vertical load is 100 kN. So average load in each column is 25 kN, and if any column carries a vertical load which is less than 50% of 25 kN, then that column should be ignored from the m value calculation. Here the second column carries around 10 kN load, so the m value for this bay is 3, not 4. Now we can calculate the phi value considering this condition, but when we apply the notional load using this phi value, all the columns carrying vertical load will be subjected to the horizontal load. There is no way to ignore a column using the notional load feature. The only solution in such a case is to apply the horizontal load manually, and this is once again time consuming. As the effect of neglecting a column depending on this criteria is very less, so at this moment we can consider all the columns and use notional load feature without any major change in results. So this is the overall process how we should consider the stability analysis according to Eurocode. To summarize, first we need to perform buckling analysis to determine which analysis method is required for the model, first order elastic analysis or second order analysis. Next, we need to calculate the initial showy imperfection value or phi value. Final step is to create separate load cases for each direction and apply notional load using this phi value. Let's check the whole process using a STAAD model. I am using the latest version of STAAD.Pro CoNNECT Edition. This is STAAD model, a G+4 story steel structure which I want to design according to EC3 code. For design part, I can simply select any analysis method, assign the design parameters required and perform the code check. But for stability analysis point of view, first I have to determine what analysis method is required for this model, whether I should go for the first order elastic analysis or the second order analysis. Then we have to apply notional load in global X and Z direction to consider the initial showy imperfection. To finalize the analysis method, global buckling factor for this structure is required. I have already applied the dead and live load cases and also created a combination load case with factor dead and live load. This load case will be used for the buckling analysis. Now I have to assign the buckling analysis command. I am going to use the eigen method, which is more accurate one as discussed in part 1. And once the analysis is performed, we can easily check the buckling factor either in the output file or in the post-processing table. We need to check the buckling factor for load case 3. So here it is. The most critical one is almost equals to 1. We can also go to the post-processing table to find the buckling factor and also the corresponding buckling modes. So for this model, as the buckling factor is well below 10, almost equals to 1, so we have to perform the second order analysis. We can delete the buckling analysis command and add the second order P delta analysis command. Now we have to apply the notional load for which initial show imperfection value is required. The height of the structure is 16 meter. There are 6 number of columns in x direction and 4 number of columns in z direction. Using this information and equation 5.5, we have to calculate the phi value. Either we can manually calculate this or we can create a small macro like this, which we can calculate the phi value on basis of the input. I have created this small VBA based macro. The equation to calculate the phi value is implemented here. I need to provide the inputs only. So the height is 16 meter, column in X is 6 and column in Z is 4. And click on the calculate tab. Now the phi value in both direction is known. We need to use this factor as notional load factor. In STAAD model, we need to create two separate repeat load cases. One for X direction and another one for the Z direction. For X direction load case, we need to add notional load with factor 0.002546. The load direction is X. So there you go. And for Z direction, once again, we need to create the notional load with factor 0.002635. Change the load direction to Z. That's all. Now my model is ready. Remaining part is common. Add the rest of the primary load cases like wind and seismic. Create the repeat load cases with combination factors. Note that as we are performing second order analysis, so repeat load is a must. To perform the design, required design parameters need to be assigned. And that's it. Our model is ready for the analysis and design. So thank you all for attending the session on stability analysis of steel structures. In our next session, we will discuss about the general instability conditions, how to identify and rectify instability and zero stiffness problems in a model. If you have not registered yet, you can register using the same registration page. Now we will open the floor to any questions you have.